Good morning, good evening, good afternoon. Since the last three videos, we've been talking about standard model, and today we'll talk about the Higgs boson. First of all, what are Higgs boson? Higgs boson are those elementary particles which are associated with Higgs field, and they're also known as the God particle. What is the Higgs field? Imagine Higgs field like an invisible medium which is spread throughout the universe, throughout the space. And in that medium, particles move and particles interact, and that interaction is what gives those particles their masses. So it depends on the level of interaction, the mass the particle will have. If a particle is interacting strongly with the field, then it will have a higher mass like W and Z bosons. And if the particles are interacting weakly, then they would have less mass like leptons. There are some particles which don't interact with this field like photon and gluon. I mentioned bosons, leptons, and all those, but I have not mentioned quarks. How do these quarks interact with this field? So, first of all, the top quark interacts extremely strongly with this field, and bottom quark interacts strongly with this field, whereas the up and down quarks interact very poorly with this field. I've been talking about the Higgs field but not Higgs boson. How are these Higgs boson associated with this field? So, for an example, electromagnetic waves. They are waves and there are some ripples in them. Those ripples actually appear as particles, and for electromagnetic field this particle is photon. Similarly, for Higgs field, when the ripple, or instead of ripple we use the term excitation, in these excitations in the field are what makes up the particle, the Higgs boson. And how do we determine how the Higgs field interact with other particles? For this we use the Higgs Lagrangian derivation. The Higgs field is a complex scalar field, and we denote this field by, this is how we denote the Higgs field. Before moving on, let me introduce you with some terms. First, symmetry. In geometry we know what is symmetry, that if we cut the figure in half it will completely overlap and all those. But in physics symmetry is not the same. In physics symmetry is something that stays unchanged after a transformation. Like for example, take a square. If you rotate it by 90 degrees, the square will remain the square. It will not change the appearance. Another term, symmetry group, is the set of all the transformations that keep the system unchanged. You can rotate a square by 90 degrees, by 180 degrees, by 270 degrees, by 360 degrees, but the square's appearance will not change no matter what you do. The square will remain the square. In quantum field theory, every particle actually fields, and these fields can be transformed, and the equations describing the physics does not change. These allowed transformation forms a symmetry group. Now another term, electroweak symmetry. At very high energy levels, the electromagnetic and weak forces are unified. They behave as one single unit. Like for example, at the time of Big Bang, when the energy level was just enormous electromagnetic forces and weak nuclear force were like almost indistinguishable. And we say that the electromagnetic force and the weak force obeys the symmetry group. Now moving on, we have the gauge symmetric group of electroweak theory. So this theory says that SU2 L into U1 Y. First, let's clear this part. SU2. It is a mathematical group describing certain rotations in two component complexes in particle physics. The particles are arranged as doublets. What is the meaning of this L? L stands for left hand. What does left hand has to do with physics? Actually, weak interactions affect left-handed particles. What are left-handed particles? Left-handedness of a particle is a property related to the spin direction relative to the motion. What is U1? U1 is simply simpler symmetry in which phase rotations occur. Involves weak hypercharges. Now what is this Y? Y is simply weak hypercharges. So we say that this entire thing has three weak fields, W1, W2, W3. We know that Higgs field is a scalar field, and for a scalar field, general Lagrangian is this, but note that I have directly skipped the conversion of ordinary derivative into covariance because it would take a lot of time. So I have directly written this, and from this formula it's visible that it has two terms. First this and then this. So what's this term? This is the kinetic energy, and second, this one is the potential energy. Now potential energy in Higgs field, what does it create? Higgs potential. And now the formula for Higgs potential is this, where this lambda is always greater than 0 and mu square is less than 0. This Higgs potential creates Mexican hat potential, and this Mexican hat potential, what happens in this Mexican hat potential is that symmetry breaks spontaneously. That's it. Let's move on to another topic, that is how Higgs field expand in vacuum or least energy regions. And if we rewrite the Higgs field, and rewriting the Higgs field, we get this, where this Hx is the physical form of Higgs boson, and by substituting this in the general Lagrangian formula, this results that several new terms appear, which gives mass and describes the Higgs field around them. That was it for today. Goodbye.